Welcome to the Omar Alayli podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to be joined by Professor Saleem Zaroubi. He is a professor of cosmology at the University of Groningen and is the winner of the prestigious Alexander von Humboldt Research Prize of 2022. Professor Zaroubi specializes in understanding the large-scale structures of the universe and the Epoch of Reionization, contributing extensively to the development of astrophysical methods used to study the cosmos. Professor Zaroubi, Saleem, welcome to the show. It's fantastic to have you here today.
Thank you, Omar. It's a pleasure to be here.
Saleem, most people have heard of the Big Bang. Now, after the Big Bang cooled down, the universe entered a period often called the Cosmic Dark Ages. Could you paint a picture for us? What was the universe like during that time?
Yeah, sure. So let me start from the initial stage of the universe. I mean, we think the Big Bang is a theory that describes the universe over its history. And if you take time back, the universe back in time, we go to the instances of its creation. And then it was very hot, and everything is incredibly ionized. Ionized meaning that there are no atoms. You have free floating charge and neutral particles as well, flying around in a very very energetic state. The temperature at the beginning was something like 10 to the 32 Kelvin, which means, it's huge temperature, and nothing withstands that temperature. Everything disintegrates, including nucleus of atoms, including the protons and neutrons inside these nuclei, etc. However, as it expands, it cools down, and it cools down in a rapid manner, relatively speaking. At some stage, it becomes, all kinds of atoms are created. The nucleus of atoms, especially hydrogen and helium, which is mostly what the normal elements are, the most abundant elements in our universe. Mm-hmm. As it about 400,000 years, or more precisely 380,000 years after the Big Bang, it cooled enough so that electrons and protons capture each other to form neutral hydrogen. Once that happens, the universe becomes transparent. So let me say something about before this stage. When charged particles are going around, they bounce together, they scatter off each other. And photons in that they scatter a lot. So if we lived during that era, we'll see the universe as opaque, as if you are inside a cloud. You don't see any details because photons don't have travel long distances before they scatter. So. Mm-hmm. However, immediately after the electrons are captured by the protons and neutral hydrogen forms, then we start seeing that the photons start roaming freely in the universe. And the universe suddenly becomes transparent, and we can see it. And so this is the first phase, and this happens when the universe's temperature was about 3,000 Kelvin, which means 3,000 degrees Celsius. I don't know what's that in Fahrenheit, but it's quite hot. It's roughly half the temperature of the sun, roughly, of the surface of the sun. Yeah. So if we lived then and we could see the universe, we'll see it reddish in a red color.
Okay.
But as it expands further, the wavelength of these waves, electromagnetic waves, the photons, gets extended because of the expansion of the universe. And as a result, they become cooler and their temperature goes down. And then we will see them disappearing bit by bit. In other words, our eyes will not be able to see them. They go into the infrared range. And if we have lived there, we will see that the universe plunges into darkness. That's roughly, very quickly, immediately after this phase of the universe become neutrons. And this is called recombination. In other words, the electrons recombine to protons. The prefix pre here is irrelevant. It's just something that people studied. It just has it's incorrect because the electrons and protons before this period have never been together, but that's the way we describe things. Anyways, so almost immediately or very quickly after this phase of hydrogen becoming neutral and helium becoming neutral, we get into this period on darkness. And actually very little happens in the universe in this period. It's just gas and matter, and that dark matter in this case, which is not exactly the type of matter we are used to, and is just expanding adiabatically. What is, in other words, in a very ordered manner, and it becomes.
Is it homogeneous?
This is something that I should have mentioned before. The two assumptions that Einstein actually introduced to the study of cosmology in his first paper on cosmology, I think it was 1916, almost immediately after he wrote the theory of general relativity, he introduced this thing we called the cosmological principle, which is basically a kind of an expansion or kind of gearing the Copernican principle towards the universe. And he said, basically, the universe should be homogeneous and isotropic. That's the language we use, which means it's uniform. No matter where you look at, it should be the same. There is no preferred point in the universe. This is in contrast to the Ptolemaic picture historically, which put Earth as the center of the universe, as a very special point in the universe, in terms of location, in terms of physics, in terms of properties, in terms of everything. The Earth in the old picture was very unique. Copernicus' big and conceptual revolution, when Copernicus came, he said, no, there's nothing, it's not special. In the solar system, the sun is more special. And that got to be expanded, saying that there is no special point in the universe. Know. So the cosmological principle is basically an expansion of that idea, saying that there is no special direction and there's no special point in the universe. All things are equal. This assumption is a very, very fundamental assumption in cosmology, in the Big Bang theory, that the universe in its very early moments was very homogeneous and isotropic, very uniform. Every point, and this every point is almost equal to the other. And this is something actually that we observe. It's observationally confirmed. So we can kind of trust that this is roughly correct. Why I'm saying roughly? Because on small scales that of at least of human beings, we see that the universe is our Earth is very structured. There are people, there are buildings, streets, there's air, so it's very complex. However, if you go to the scales of hundreds of millions of light years, then the universe would look roughly the same wherever you look at. Below that, there is a structure, and this assumption breaks down. But this is one of these big assumptions. Now, so to go back to the story I was telling, is that when the universe plunges into this period of darkness, where nothing is just gas, homogeneous gas kind of expands with the universe and cools down, and almost nothing happens except one thing. So okay. And that thing is that the following. When the universe started, we said that everything was almost homogeneous. However, there were very, very small fluctuations, very small differences between one point to the other. And they are really small. They are of the order of 1 to 100,000 when the universe was 400,000 years old. So they are tiny, tiny fluctuations. Some of these fluctuations are bigger than others. And those fluctuations, they have a little bit more matter inside them. So when you have a little bit more matter in a kind of in a volume in the universe, in a kind of limited volume, you'll have more gravity than other places. And then in some of these points, gravity actually starts overcoming the expansion of the universe and starts pulling things together. Okay. These are the sites of the formation of galaxies. This is where galaxies start forming. Galaxies are these fluctuations in this matter that have enough gravity that it overcomes the expansion of the universe. So within a galaxy, which we see, there's lots of galaxies. Within a galaxy, it's like this is a name that the philosopher Kant gave them. He didn't know about what they are really, but he thought of them as island universes, which means they are things that kind of got separated from the expansion of the universe. So within a galaxy, there is no expansion of the universe. However, other galaxies relative to each other, they really get further and further away from each other. Okay. So this period, when galaxies start forming, they start ionizing the universe. In other words, they have this UV radiation that separates again the electrons from the protons, and that process takes a kind of long time. The whole thing, after 1 billion years from the Big Bang, the universe is completely ionized again. And this is the period I normally study, is the first 1 billion years of the universe. Professor, your work, like you just said, delves into the period cosmologists call the cosmic dawn and the epoch of reionization. For our audience, many hearing of these terms for the first time, what was happening in the universe during this critical early phase, just a few million years after the Big Bang? Yeah. So these three periods are part of this first 1 billion years that I just mentioned. And we separate normally to three eras. The first is this dark ages. This dark age when things plunge into darkness and there are no sources of light, so to speak, to light of to shed light on the universe, etc.
Mm-hmm.
That was called the cosmic dark ages. It's a cute name that was given by an American scientist called Walt Sargent, and it got popularized after that. Now, after the first objects that start kind of pulling together the material, they get compressed by gravity, and gravity kind of causes all kinds of things to happen, including star formation.
Mm-hmm.
And this is the formation of the first objects, first stars, first galaxies. And once these objects start forming, they are very different than the stars that we are used to today because of their composition. Their composition is very different than the sun. They are called population 3 stars or first stars. And they are mostly from hydrogen. So hydrogen has special properties that make it very hard to make simple stars. They have to be a little bit more massive. That's what we expect, very massive actually. And once these stars form within these first galaxies, they start emitting ultraviolet radiation, and that radiation started heating the gas a little bit around it, ionizing as well. But it's not enough to ionize everything. They ionize a little bit around them, but they start kind of heating the gas, just making it. So if we look with a special type of radiation called 21 centimeter, which I'm sure we'll talk about it more. And this is a radiation that comes from hydrogen. Suddenly, we start seeing a difference in the regions around these stars in this radiation, in the 21 centimeter radiation. We start seeing a difference between that part of the sky or the intergalactic medium and other parts. And that the main difference is in the temperature. So this period where the main thing that you see is changes in the temperature is called the cosmic dawn, because it happens, this is the dawn of formation of first objects, of first stars. However, with time, something like 700 million years after the Big Bang, you start having more and more of these things, of these objects, of these galaxies, of these first types of galaxies. And they're scattered, they basically start spotting, kind of scatter all around the universe and filling it bit by bit. And the UV radiation then starts being enough to ionize large swathes of the universe, large regions of the universe, and heat the other parts. So that what you see, the dominant phenomena that you see when you look at hydrogen is that you have some areas that hydrogen is completely ionized and some areas that are neutral. Of course, it starts little by little. First, small areas that ionize, and most of the universe is neutral. And later, bit by bit, you have more and more ionized regions and less neutral regions, until the ionization becomes complete, almost complete, at about billion years after the Big Bang. So that's something like 13 billion years ago. And that's the end of this period of so the last period, we call it the Epoch of Reionization, because the dominant physical process is the ionization of gas. And so we study its properties and why it has these properties and not these properties, and not other properties, etc. So this is the first billion years, and these are the 3 eras within.
So why is understanding the transition out of this era, the cosmic dawn, and subsequently the Epoch of Reionization, so fundamental to understanding everything that followed, including large-scale structures and how galaxies like our own Milky Way galaxy came to be?
So that's an excellent question. So the importance of these periods stems from a number of issues. So let's now think about the universe before this. Before this period, there was no astrophysical objects. Everything that happens in the universe as a whole entities, things that happen everywhere. As I said, the universe is homogeneous and isotropic, and it happens as a global phenomenon. This also happens as a global phenomenon. However, the driving force or processes that make this happen have to do with astrophysics. Before this period, there is no meaning of talking about astrophysics, because astrophysics didn't exist. What existed before is just a universe that behaves as a whole entity. These are the first astrophysical objects: stars, galaxies, planets, etc. So that's the first important thing.
So moving from quantum physics to general relativity.
Quantum physics is always important. But in different ways. The main thing in this period is that gravity becomes the local fluctuations and their gravity become very important, so that structures start forming in a very coherent way. This is the first time where a tiny component of the universe, which is about 5% of its components, which is called baryons. Baryons are things that actually it's a generic name that physicists give to things like protons and neutrons. It's everything that has an odd number of quarks inside them. So that's a technical thing. But it's protons and neutrons are part of these types of objects. So we are made of baryons. When we talk about baryons, we are talking about normal matter. And we know that baryons, our kind of normal material, constitute only 5% of the universe.
Okay.
So this is a phenomena that is first time in the history of the universe that is dominated by baryons alone. I mean, that's this is a phase transitions that driven by baryons. Of course, baryons were important in earlier stages, but they traced other things before. Here, it's something that it's gravity and baryons that do all of this stuff. And you start having these stars and the first galaxy stars and galaxies. So that's the first thing. The other thing that is very important is that when structures start forming and stars start forming, you start creating heavier elements than hydrogen and helium. In the early universe, the universe produced overwhelmingly, I mean, by many orders of magnitudes, only hydrogen and helium. Here, hydrogen is something like 75% in mass, and helium is about 25% in terms of mass. The rest is actually negligible. Is 1 in 100,000, 1 in 10,000, and even much much smaller. So you don't have the carbon, you don't have the oxygen, you don't have the iron, you don't have anything that the gold, the platinum, nothing that we are used to is formed in the early universe except hydrogen and helium. So for that to form, you need to form the first stars. Why are the first stars important? Because stars actually work by burning inside them, nuclear burning, lighter atoms and make them heavier atoms. So what happens in our sun, for instance, the sun constantly transforms 4 hydrogen atoms to 1 helium atom, or more accurately, 4 hydrogen nuclei to 1 helium nucleus. And that process, which is a complicated process that took us, this is one of the main achievements of astrophysics, is to understand this process and how stars work. It creates energy in the process and creates new elements, a new nuclei of elements. Another process that happens not in the sun, because the sun is a small star. In bigger stars, for instance, you have helium at the core. At some stage, helium becomes the most kind of dominant thing in the core. After some stage of burning, you burn off all the hydrogen, and in big stars, in more massive stars than the sun, all what you're left with in the nucleus of the sun, you end up with helium, and then helium starts interacting with each other if you have enough gravity. So that's why you need more massive stars than the sun. And then you, for instance, take 3 helium nuclei and make them interact together. This is called triple alpha interaction, and that makes carbon. And we are made of carbon. So this phase that we are starting to talk about is the first phase of star formation that kicks off the later formation of later stars and formation always of heavier elements until you get to iron. I mean, stars inside them, they cannot make that more than iron. And every time you have this creation of elements, stars die. And when they die, they somehow get these materials from the inside and diffuse them into the interstellar medium. So the next generation of stars will be enriched with more of this stuff, and will enrich after it dies, will enrich the environment more, so that when you get to a star like the sun, which is a 3rd generation star, you have enough carbon, enough iron, enough oxygen, and etc. to have life. So this is a first step, and I want to emphasize this. This is an amazing thing that happened in the last 100 years, and especially in the last few decades, is this link between the universe, which is homogeneous and isotropic and its inception. But we have a very detailed story. Of course, not all of it clear. We have still gaps. That's why I do my research. From this period, which this universe, which is very alien if you think about it to what we kind of are used to, down to planets and life. I mean, this is amazing. We have a story and it's not a story, it's a scientific story. It's not just a story we tell. It has a lot of evidence that connects all of these types of things. So this is the other thing that for which we study this type of there are many other reasons. For instance, the first type of stars and galaxies are different from later ones. So that's so I mean, we don't know how much of them is controlled by black holes, big black holes. We don't know how many, what that exactly type of stars, how efficient the star formation is, how efficient the radiation, what's the spectrum of the radiation that comes out. So these things we don't know enough. So that's very important. So for astrophysics, this is very important period that is we lack information about. We are trying to study. There's another aspect in all of this, which is if you look at these three periods and you can detect them, they link you in a very direct way almost. It's very hard to study these periods observationally. They are very difficult, and we'll talk about this probably. But they give you a link to the earliest points in the universe because they carry the imprint of the initial conditions of the universe, how the universe starts. So on top of all of its astrophysical importance, of its it's a period in the universe that we need to understand that we don't understand, its ramification to further star formation and galaxy formation, etc., etc. There is this very intimate link between what we see and the initial conditions in the universe, which we would like to exploit to understand these conditions. What does it say about cosmological inflation? What does it say about other kinds of properties of the universe that are linked to its inception, to its initial conditions? So it's in many ways, it's very interesting. And I'm sure I'm skipping all kinds of reasons to study this, but it's a very, very exciting field of study.
You've dedicated much of your research, particularly through major international projects, to understanding this era. What are the absolute biggest questions about this epoch of reionization that scientists like yourself are trying to answer right now?
Right. So let me tell you how we try to study it first, and then kind of turn your question, because that's related to it. So as I said, because there are no stars and galaxies very early on and very little later, it's very hard to see stars and galaxies. Galaxies, especially in the dark ages, there is nothing of that type. In the cosmic dawn, there is a little bit. We hope to see of them directly by JWST or something like this, but it's difficult. They are starting to see some of these high redshift galaxies very early on. Galaxies, that's what we call high redshift. It means very early on, very far away, and with JWST, so we'll get some clues on that. But the best tool to study these periods is something called 21 centimeter emission, and it's an emission that comes out from neutral hydrogen, only neutral hydrogen, or atomic hydrogen. You know, the air that we breathe has molecular hydrogen, H2, right? You have hydrogen that's connected to hydrogen. So that doesn't emit this type of radiation. You need atomic hydrogen, which means bare atoms that are not connected to anything else. In that, there is a process, it's a quantum process, which is a forbidden process. So forbidden in the sense, in quantum, there's nothing forbidden. It means its chance of happening is very, very small. And this has to do with the spins. Each particle has a spin, which classically has this equivalent of something spinning on its axis. It's not exactly that, but that's the best analogy. So the proton has a spin, and the electron has a spin. And so you have in hydrogen, you have proton and electron, and the spins have two options. Either they align together in the same direction, or they anti-align. And it turns out that the anti-alignment ones is the lowest energy state. And this one is the excited energy state. And so if you have a hydrogen atom that has a proton with this direction and an electron with this is excited states, which means energy is not exactly at the lowest level. And nature likes to go to the lowest energy level, so they like to do this. But this takes for a long, long time. So if you have one hydrogen atom in this situation, to go from this to this, it takes something like a million years. I think it's 10 to the 15 seconds, which is roughly a million years. So it's very unlikely to happen. However, because you have so much hydrogen in the universe, as I said, the dominant atom in the universe is hydrogen. You have enough of those that emit, right? And the wavelength of this transition, it emits electromagnetic wave with a wavelength of 21 centimeters.
Okay.
So which is in the radio regimes. 21 centimeters is a big wave. It's not like a kind of optical light, which we're talking about a few thousand angstroms and things like that. This is really big. So for this you have to go to large. More than that, because the universe expands, if you have a 21 centimeter emission from far away, from redshift 10, redshift 10 means the universe was smaller than its current size by a factor of 10, roughly speaking. It means that this 21 centimeter had to expand 10 times more until it reached us, because the universe expands, right? And remember, when the universe expands, it's not that galaxies get away from each other. That's not the picture. This picture is wrong. What happens is that the geometry of the universe gets stretched. So everything with it gets stretched. Including these wavelengths, these frequencies. One can explain them in a simpler way, but let me not go into that too deep, because we will not finish. So you get this 21 centimeters stretched from redshift 10, which happened about 13 billion years ago. That means that what we get is roughly 2 meters wavelengths, right? If 21 centimeters multiplied by 10, that's 2 meters and 10 centimeters. So you are in the radio. This is radio frequency regime. This is radio astronomy. And this is actually low frequency radio astronomy. That's really the lowest of the lowest energies. And so this is what we study. We study radiation that comes from these objects, from the neutral hydrogen in the universe before it got ionized, right? And we look at it and we see it at the beginning. In the dark ages, we see its properties, if we can see it. We cannot see it now. Now, all of this is in principle. I'll explain to you why it's so hard. It's a very hard thing to do. When you go to the cosmic dawn, you see heated things and not heated things. Then you see its imprints on the 21 centimeter on hydrogen. And at the end, in the Epoch of Reionization, you start seeing that these things disappear. This radiation disappears bit by bit as the universe becomes more and more ionized, because you don't have atomic hydrogen anymore. It becomes ionized. It's protons. And so this is what we try to measure with radio telescopes that are specifically designed for this. Yes.
Okay. So by tuning into different frequencies of this 21 centimeter signal, it's like tuning an old radio to different stations, but instead of music, we're potentially hearing echoes from different moments in the universe used.
Right.
What specific information about the cosmic dawn and reionization, things like temperature or clumps of gas, can this 21 centimeter signature actually reveal?
Yeah. So that's a very good question, and your analogy is very apt. Basically, is very good. Listening to music at different frequencies. So again, I want to emphasize for the untrained, kind of audience, when you talk about 21 centimeter, that's a very specific frequency. It's 1,420 gigahertz. So when it's emitted with these types of properties. But as the universe expands, they reach us with different properties. Now, we can use the frequency to decide where this radiation comes from, because the older it comes from, the farther away it comes from, the more stretched it is. So it will have a different wavelength, therefore different frequency. So different frequencies tell me a bit about the history of the universe. So each slice in frequency tells me a different time in the history of the universe. So this is why we translate time, this frequency, to time. So we have this temporal information, time-dependent information that tell me about the evolution of the universe. So that's the first thing. The second thing, when we look at a certain patch of the sky, we look at the intergalactic medium. That's the medium between galaxies, not inside galaxies. That's just the diffused material which is in the universe. And when we look at it and we see more contrast between a certain point and the other, very large, it will tell me which one of them is ionized and which was in neutral, because the ionized one, I will see nothing, basically. Where the neutral one, I will see a lot.
Okay.
But we look in with interferometers, and interferometers, they are sensitive to differences, not to absolute values. So I know that the differences are high. So when I'm looking at the period where I expect the Epoch of Reionization to happen, then I see these contrasts, and they are very big when the universe is half ionized, half neutral, because you have, But bit by bit, when the contrast goes down and down, at the end I don't see anything. That means the universe got completely ionized. So I get the history of this this process. So that's one. Another thing that we get is the size of these ionized regions. If we look at the size of ionized regions, it tells us about information about two things: about the hardness of about the properties of the radiation that causes the hydrogen to ionize. So if you have stars, what type of stars they are, what type of radiation they are. And also it tells me a little bit when I look at the heated stuff, when different patches have a little bit of different temperature in the intergalactic, it tells me a lot about the role of X-ray sources. X-ray sources are very good at heating, and X-ray sources are normally associated with black holes and neutron stars. So these are very high energy emitting objects that cause these things to be emitted. So we learn about the properties of the sources. We learn about how fast it happened. We learn about the scales it happened. The first thing that we look at is something called a statistic called the power spectrum, which tells me what is the different strength, what's the contribution of different scales to this, what are the important scales, etc.
Okay.
So there's lots of information about this. I must say that currently we have been trying to measure the 21 centimeter from these epochs for a very long time. There are tentative kind of claims for detection, but none of them are confirmed, and they are probably not correct. I mean, that's my view, at least. It's a very difficult measurement. So currently we are in this, at least my mindset, and I think for many, is that of discovery. You want to see this effect. And then later we would be kind of, the field will be geared toward understanding the ramification and the implication of what we see. But at least to have a detection, to see that there is something that we can kind of hang on to say, we got it. We have been 20 years in this, and we are getting close. We're getting very close, I think, but we're not there. It's still not there yet.
So detecting this 21 centimeter signal is notoriously difficult, as you said, and requires extraordinary technology. It's often described as finding a needle in a cosmic haystack. You were instrumental in co-founding and leading the Epoch of Reionization key science project for LOFAR, the Low Frequency Array, a massive radio telescope array. Could you describe LOFAR? What makes this giant radio telescope, which spreads across Europe, uniquely suited for this incredibly challenging task?
Right. So as I said, you need these detectors that go into meter type of wavelengths. So to go to meter type of wavelengths, it means that you need to detectors of this size, at least 20 centimeters, 30 centimeters. At least you detect part of the wave that comes to you. The initial detectors that we have to be sensitive to that. But that's not enough. You need also to have a lot of detectors, because you need to be sensitive enough to this radiation. The problem of this radiation that we have been talking about is that it is so feeble. It's incredibly small. The effect that we expect to measure, at least from the Epoch of Reionization, it's even more feeble. This radiation is very feeble, and it's so feeble. To give you an example, what we expect to measure is a radiation of order of 10 millikelvin, 5 millikelvin. We always measure it in terms of energy, which is a shorthand for intensity. It's how strong is the radiation. Our galaxy alone, in these frequency ranges, contributes 1,000 to 10,000 times more. So you have this mountain of emission from our galaxy that has on top of it this small radiation, and you want to disentangle one from the other. So it's a very difficult measurement, but that's not the main difficulty. The main difficulty, I can go into difficulties forever, but the main difficulty is that this radiation, as it comes to us and goes through the ionosphere of Earth, which is the atmosphere, it's part of the atmosphere of Earth, which is ionized. So it's called the ionosphere, and the ionosphere causes these radiation it scrambles it. It causes it to dance. And you want to understand how to fix that. And that's not easy. That's really the main difficulty. But this is a very difficult problem that we have been trying to solve for a long time. Now, having all of that, then you have the detectors on the ground. The detectors have to be big. But because they are the sensitivity has to be big, you have to put tens of thousands of these detectors. It's not one or two. You can distribute them in different ways. They have to cover large area. They have to have large distances between them because you need a resolution. That's the distance between these things give you the resolution, how accurate you can measure things, but also how dense is the filling. They are filling. It gives you the sensitivity. But of course, you have a certain amount of euros or dollars to spend. So you cannot have an area which is completely filled for tens of kilometers. That just doesn't happen. It's just too expensive. So you have to be clever about how you design, how distribute your antennas on the ground. And so we cluster together a certain number of antennas. We have them by, we put in on 4x4 types of things, and in these 4x4 things, we cluster together to have 16 of them together, and that's what we call a station. That's something. This is our unit of detection, and then a similar unit will be somewhere else, and then you do what we call interferometry. In other words, you get a radiation here and a radiation here, and see what is the similar part. That's the correlated part. That's the kind of technical term. And so you correlate between them. That gives you a measure of the changes of the sky, of that part of the sky than other part of the sky within the resolution of that is decided by the distance between these two things. So the LOFAR project was a project that was kind of designed back in 2004 we started, but it has a number of scientific targets. One of them is the Epoch of Reionization. There is other kind of different science cases for this that use the same technology more or less. So you also have to compromise between different sciences. So we have a part which is it's called the LOFAR core. That's a very high density of antennas that we put at a certain area, something like 50 kilometers south of Groningen, the city of Groningen, where the university is there. And then there's other circle of things, other kind of baselines, what we call other things scattered within the Netherlands. These are kind of within 100 kilometers. You have also a lot of them, but then within 200 it becomes less, etc. And then there are antennas that are or stations that are positioned in different countries. We have Poland, in Germany. Germany has a lot of them. There's one big, huge station in France, in the UK, etc., etc. So, and those are used for different purposes. The ones we use for our projects are the one in the Netherlands, within a few hundred kilometers. This is because you, as I mentioned before, you not only need the resolution, you need also the sensitivity. So we cannot fill the whole of Europe with antennas. You have to choose a certain areas, and the area that we chose is around that area in the north of the Netherlands. And the main difficulty is, as I said, you measure. We started measuring things in 2010, roughly 11, and accumulated a lot of data. And we are struggling with cleaning it, with separating the signal from the different components that come into it. And that has proven to be a very difficult task. We have something like 4 petabytes of data, which is huge. I mean, it's just, I think when we started this project, we asked where we will put this petabytes of data. And we estimated that just storage alone will cost us millions of dollars or euros. Luckily, Moore's law kind of caught up in this, and now it costs us to something like tens of thousands, up to 100,000 euro, which is something that you get on a grant. There's no problem. It's not like millions. The same story with the computation. We started with asking, how do you compute all of that stuff? It's huge. It needs dedicated supercomputer for many years. Luckily, we discovered the GPUs very, very, very early on. I think 2005 or 6, we started using GPUs. We were one of the first to start using GPUs for this type of number crunching, and that improved our life quite a bit. So now we can analyze this data. We can go through these petabytes of data, not only store them, but actually go through them with these types of machines. Of course, GPUs, I don't know if people know about the GPUs, are good for certain types of calculations, but not good for others. Luckily, most of our calculations can be adapted to GPUs, and that saved our lives. Instead of buying computers, supercomputers with tens of millions of euros, a few stations of 300 thousand GPU stations, and that's feasible. But we have been analyzing this data since.
Okay. Well, this sounds like listening to this signals is like trying to hear someone whispering across the stadium during a rock concert. Developing the techniques to subtract this noise and calibrate the instruments must involve incredibly sophisticated data analysis, like you alluded to. Can you give us a sense of the complexity involved in processing the sheer volume of data LOFAR produces?
Yeah.
To even hope to isolate this signal?
Yeah. I before talking about this, I should mention that currently there are a number of projects. There's there's a community that does this. We were probably the first or the second. There's one project before us, Chinese, but didn't survive. We are the first to start this project, but now there are a number of them that are trying to do it. So there is some type of competition, but also a collaboration because we face similar projects, similar problems, and there's a community of people who are doing this. There's some American ones. There's an Australian one. There's something futuristic called SKA, which was not so futuristic because starting being rolled out, which is a collaboration between many countries. So LOFAR is not the only one, but we all face the same type of problem. The problem is how you separate this few millikelvin things out of this 1,000 millikelvins. Especially with this scrambling. So in principle, you can do it because you know the properties of the emission from the galaxy is different from what we are trying to detect. And the simplest analogy which I like to give is like looking at a tree at the top of a mountain, which is roughly kind of works out into be the same number of order of magnitude. So if you have a mountain, it's 1,000 meter kind of thing. And if you have a tree on top of that mountain, which is 1, 2, 3, 4 meters, you can see it. You can say that's a tree. I mean, that's no problem. Why? Because you know the property of the tree, and you know that that's not part of the properties of the mountain. Similarly, this is what we want to do. When you look at the universe and you look at this 21 centimeter, you have ionized regions, not ionized regions, ionized, etc. You expect things to go up and down along the line of sight, whereas the properties of the galactic emission, it comes from something called synchrotron emission, which is a certain kind of electromagnetic emission that comes from these fast electrons and that accelerate or interact with a magnetic field. This synchrotron radiation has a very smooth structure in frequency. So our thing goes up and down, whereas the frequency, the synchrotron is very smooth with frequency. So that's the hope that you can separate both. And we think we can do it. This is one of the first things that we tried, whether with the sensitivities we have, we can separate the two things. There's also noise, like when you open the old TVs, when you see this salt and pepper type of pattern.
The white noise.
The white noise, that's white noise basically, which is inherent to any measurement. That's the inaccuracy of the measurement. That's how accurate you can get, and it's also always limited. So that's the other thing. But however, the most complex thing comes from the atmosphere, from the ionosphere, which as I said, and that is a very difficult thing to do. The reason being is in optical astronomy, people use this. They call it adaptive optics. So you want to look at the sky, and you see all kinds of objects, sources. But the atmosphere in adaptive or in optics, in normal optics, the atmosphere have these turbulence. So it mixes a little bit. So you lose resolution. So you cannot see objects very, very clearly within this turbulent cells in the areas in the atmosphere. So what people do, they use what they call guiding stars. So you have a point that you know it's a point that is close to the thing that you want to observe, and because that's a point, when it gets to the atmosphere, it gets scrambled and it gets kind of widened. You know how to fix it because you know it's a point. So I know how to turn what I observe back to a point, and then I use the same thing and apply it to the thing I want to observe. So assuming that what happens to that point is exactly what happens to my guiding star. So that's the trick in a simple. So this is it's similar to what we do, not in the atmosphere, however, rather in the ionosphere. And it's not one star, it's a huge area. And there's another thing which is very technical, but I have to mention it because it's part of what we do. when we measure in these radio antennas, these radio antennas look like this. They are two things that are, so they have what we call polarized response. In other words, they measure the strength of the electromagnetic wave in two directions, this and this.
Okay.
Now, even if your radiation is not polarized, in other words, it doesn't have a preferred direction, your response is polarized. It has a preferred directions, and you can fix that. The problem is, and again, that's a bit technical, is that the synchrotron emission from the galaxy is very polarized. In other words, it has preferred directions. So once you measure and you want to correct for this effect, you don't know if you are correcting it correctly or not correctly. And in other words, you scramble the polarized and the non-polarized part. And that can kill you. That just can hide the whole effect. So this has been our struggle for 20 years. It's trying to find the best solution for this type of thing. And the best solution come from adaptive optic kind of solution. And that's you have guiding stars. We didn't have guiding stars at the beginning. Now we do have a map of the sky that we think we understand. These are not stars, they are galaxies normally. That we have been studying for a while and correcting and perfecting and etc. And we use that, right? It took us many years to build and it's not perfect yet, but use that as our guiding stars so that we can fix the scrambling of the ionosphere and separate these two things from each other, the polarized and non-polarized stuff, to get to the signal. And this has been a very, very difficult thing. There are other things that are important here, which I don't want to get too technical. For instance, the beam. If you have a telescope, a normal telescope, you have optical telescope, it's structured so that its mirror is elliptical. So it naturally has one focus point and everything goes to that focal point. In these types of things, you have to build from these scattered antennas a beam, what we call a beam, what we see, how it's the response of our telescope to the sky. Of course, the center will be very sensitive and the rest will be more not so sensitive. So if you have noise and not very perfect coverage, you have a complicated beam that changes with time, depends on the electronics, because you are all your antennas are outside, they are prone to the elements, to weather, to rain, to whatever, to rodents even in the field and stuff like that. So you have to take that into account. And if your beam, the one that you reconstruct from your measurements, is not stable, even to the 1 in a million, you will not get to the data. And this is something also we have been struggling with, and we have been solving. I mean, all of these things are surmountable. We know they are surmountable. Otherwise, we will be wasting our time.
Yeah.
But they are taking our time. So currently, we are getting very close. I think the community in general is getting closer and closer to the level of understanding of each of us, of our instruments, and how to understand their complexity, so that we can use that in order to understand what we are measuring in the sky. So that's the difficulty. It's a very technical issue, but it's a kind of formidable issue. It involves mathematical problems that are what we call inversion problems that are very difficult. It involves the project involves computer scientists, applied mathematicians, radio astronomers, radio engineers. It's a very multifaceted type of project, and this is what you need.
Although, these are really seriously very challenging issues that you overcome. However, the project has produced significant results, overframed as upper limits.
Right.
Could you explain what an upper limit means in this context, and why even not detecting the signal at a certain strength is significant also?
Yes. So this is poor man's result, if you want, but it's very significant. So let me give you an example. Again, it's for non-scientifically trained person that is listening to us or seeing us. If I want to ask, does a certain city have a skyscraper, right? And what is the highest skyscraper or high-rising building that this city has? And I have a crude picture of that. Then I can say, okay, the picture is so crude that I cannot distinguish between the buildings, but it cannot be more than 100 meters or 200 meters, because that I would see even with this hazy stuff. So you say this city doesn't have anything higher than 200-meter skyscraper or high-rising building. And so that's the type of the upper limit. Upper limit says not what there is, but what there is not, right? What is excluded. So I can exclude things that are, kind of like the needle in Dubai or whatever. That's just not in that city, but maybe something like I don't know, 50-story building. That's still possible. So as you clarify your picture, kind of gradually, you start being able to constrain things more and more accurately. So you say, oh, now at 200 meters, I knew that there is nothing more than 200 meters, but now the picture is clear enough to say that I don't have anything higher than 100 meters and 50 meters, until you get to where I now have a picture that's clear enough that I can say the highest rising building is 50 meters high, period. And that's a detection. But before that, all what you say are upper limits. It cannot be higher than this. It cannot be higher than this. And that's very important, because as you go through that, you can say, for instance, again, I'll go with this analogy, which I just thought of it, which is actually a nice analogy. You can say, okay, this city cannot be New York because it doesn't have anything higher than 200. So you rule out all kinds of models. You say this city is not Seattle because it doesn't have. And you go through the list at least. So you rule out the extreme models, the things that have these very high rising buildings. But you cannot rule out most cities, because most cities in the world don't have these, unless you really see in high resolution what is there, and then you can say, oh, this is clearly, I don't know, Nazareth, which is my city, or Palo Alto,
Amsterdam,
or whatever. I mean, it's a certain features that you can distinguish, and this is what we are trying to do. So these upper limits are good in excluding cosmological models that produce these extreme fluctuations. So now we can say that very extreme fluctuations are unlikely; they are not there. So you rule out some of the models of first galaxies that give you galaxies and black holes that are very extreme. And so that's a very significant contribution, a significant advance. But it's not still the detection. Detection is really to know the properties, not to rule out properties that are not there. So you really know. So it's a different mode of operating, of thinking. So now, so far, we are looking at upper limits. We are ruling out models that cannot be. But once you go, so we are now, I think the best sensitivity is about 30 millikelvin, something like this. We have it in LOFAR. There's a American project called HERA. It has better results so far in the last few years. And that they are of the order of 20, 30 millikelvin. But that's not still good enough to reach the 5-7 millikelvin. But we are getting there. But all these projects are getting there. And hopefully within the coming few years, we will get there. And then I will not say that we are able to say that the height is 7 millikelvin, rather than saying it's less than 20 millikelvin or something like that. So it's a very different statement. Although the less than 20 millikelvin is very useful because it excludes all kinds of things. I hope this is kind of clear enough.
Saleem, the epoch of reionization didn't happen in isolation. It occurred within the grand structure of the universe that was forming at the time. You yourself made significant contributions to mapping this universe's large-scale structures, like the cosmic web. You developed innovative techniques like the Wiener filtering and the UMV estimator to reconstruct this structure from incomplete data. How does your work on reionization connect to our broader understanding of how large-scale structures like galaxy clusters form and evolve?
Okay, so this is... let me start with the differences first. I mean, the thing that I started, this is what actually came out from my PhD, mapping the universe, or techniques to reconstruct the universe's density distribution and velocity distribution at what we call redshift zero, which is now around us. Around us meaning within 300 billion light years. That's big, but it's small in cosmological terms. Whereas when I talk about the reionization, I talk about very early on, 13 billion years ago. I mean, so it's a different era. The link between them is the more conceptual link. So the mapping of the universe at low redshift and the formation of galaxies at the early on all comes under the same banner, which is called large-scale structural formation. And this is one of the most significant advances in cosmology in the last 30 years, 40 years. As I said previously, when you look at Einstein, when Einstein started writing his theory about the universe, or more kind of the later ones like Friedman and Lemaitre in the early 19th century, all of them talked about the universe as a whole kind of entity. A homogeneous, isotropic, it has one density at any time, it has one temperature at any time, etc., etc. However, linking the universe to what we see around us is this topic of structure formation. This is how these fluctuations, how this universe that's very homogeneous and isotropic came to evolve such structures like galaxies. Galaxies are scattered in something we call cosmic filaments and clusters of galaxies. There is a whole hierarchy of structure that we talk about normally. So my scientific career has been kind of mostly geared into that direction, understanding how structure forms and links the basic level of cosmology, if you want, with the observational level of astrophysics. So this is one of the biggest advances, and I was lucky enough to come in a period where this is flourishing. I mean, I was one of many people who contributed, and this has been kind of rewarding. Maybe, but the point of principle is linking these two things, astrophysics and cosmology, were not linked before the last 30 years. Now we have a clear link how galaxies are formed. We don't understand all the aspects, but we understand the processes, kind of the broad processes very well. How stars form, how planets form, and how we formed, etc. There is this clear kind of physical story that tells us level by level, in terms of time and in terms of scale, how things formed and why we our small kind of part of nature, the Earth, it looks like it looks, the solar system looks like it looks, and that's a very important aspect. But all of this stuff is linked into one in the same physical kind of picture, which is how the fluctuations, which started very tiny, these kind of disturbances in density, grew with time, first to form the first galaxies, that's the first billion years, the Epoch of Reionization, cosmic dawn, etc. But then how they evolved further and further to develop these very, very structured things around us at the large scale, which we see that these cosmic filaments, these clusters of galaxies, voids, etc., and us.
Yeah, cool. So there's a lot of buzz right now around the results from the James Webb Space Telescope coming in, which is peering into the same early cosmic era, sometimes finding surprisingly mature-looking galaxies very early on. Some even talk about a potential crisis in cosmology. How do these JWST findings, which look directly at the source of the reionization, complement or perhaps challenge the picture you're building by studying the gases with LOFAR?
Right. It's an excellent question, and I must say JWST has been we've been surprised. Nature always surprises us in many ways. However, I don't think we are in a crisis yet. I mean, we are really far from crisis. It's so I'll tell you what is the difference. So when JWST looks at the universe, it picks up the brightest objects. So these brightest objects that are easy to see, because it's challenging. You want to push the envelope, so you look further and further in time, and you pick up these very, very bright galaxies early on. So these are the tip of the iceberg, if you want. They are even not the tip of the iceberg. They are the tip of the tip of the tip of the iceberg. These are really the highest things. And those you observe and you ask yourself, do I expect in a cosmological theory these objects to form already? So that's a fundamental question. And the answer is probably yes, because there are, the cosmology still allows these models to form. However, do they challenge our understanding? Of course they challenge our understanding because we didn't expect this. But again, this is galaxy formation. Galaxy formation is very messy, and there are lots of ingredients that we haven't thought of. Now, if JWST or some other instrument, JWST cannot do that, tells us that there is a galaxy at redshift 50, which means that when the universe was 50 times smaller than its current size, then that's a crisis. That's a crisis in cosmology. But so far, we are not there. It's a challenge to the models of galaxy formation, which we don't understand fully, completely, especially the formation of the first galaxies. more mature, more later on galaxies, we have better understanding. But the first galaxies are very problematic because of the lack of, we don't understand also the first stars. That's why I don't buy all of this kind of that we can interpret the sources immediately from what we look. It takes time. It takes more time and more understanding. So the way I look at this is that it's another kind of piece of evidence that we have to put in this comprehensive picture that we have found. So that's one. The second thing is that because these types of telescope like JWST looks at the tip of the iceberg, really the most massive things, it doesn't probe most of the universe. The Epoch of Reionization is about ionizing the bulk of the universe, the most, kind of the most mundane types of things. And that is not probably done by these objects. These objects cannot do that because they are rare. Though we can see them, they are still not so abundant. They are done by smaller galaxies that we don't see. JWST doesn't see these galaxies, and they might have different properties, different types of things. There is lots of information information that we don't know yet about the relationship between finding a galaxy and finding how much of its ionizing radiation comes out. It's just not clear that you see a galaxy and you ask, okay, I saw a galaxy, but how much of this UV radiation, which is the ionizing radiation, comes out?
Okay.
Or the heating radiation comes out, then it's not clear. So you have to make all kinds of assumptions and go with that. So far, I think GWS has surprised us because our normal models were not that sophisticated to expect that, to find such galaxies, but they are still within the limits of what is allowed.
Okay.
Maybe we get to a limit that is not allowed, and that allowed in the sense if you assume normal cosmology, and then you are in a crisis and you have to explain things. It's like in evolution, if you say, okay, what kind of constitutes an evidence against evolution? So the normally the answer is a Precambrian rabbit. So if you find a rabbit that is just lived in the Precambrian period, then that's clearly evolution didn't work in the way we think, or life didn't evolve the way we think. So we are not there yet, and we are far from there, I think. And also JWST, there's lots of buzz around it, and many times, and it happens quite a few times, at the initial stages after the telescope became operational, they saw galaxies that they claimed that they are range of 17 or something like that. It just turned out to be completely nonsense. It's not right. These are objects that they misinterpreted, and they are actually at redshift 2, which is much, much closer. So not 2, maybe 3, 4, I can't remember, but it's much, much closer. And then you don't have a problem. So we'll have to wait. Science needs mature, not only to see new results, but you also need time to confirm these results and to put them on a kind of solid footing to trust them enough to validate about it. And that goes for what we do as well. And 21 actually, people have to be more skeptical than I would be. Much more skeptical, because it's a much more difficult thing to claim. But we'll see. Once we get to there, we'll see if we can convince the community that we ourselves first, and then. And I am one of those that think that before going to excited things, to controversial things, just explore what you can do, because the universe is complicated as it is. You don't need to complicate life more. Of course, if evidence is pushing towards these models, of course, we'll have to go with that. But I don't think that still is not at that level yet. Yeah.
Okay. Can we talk about the CTP symmetry? Like CTP for our audience stands for conjugation, parity, and time reversal. So with CTP symmetry, researchers can postulate a mirror universe. In other words, a two-sided cosmology, where time is not added after the Big Bang, actually like in general relativity, but rather it's an emerging factor because it emerges out from both directions in the universe and in the mirror universe.
Yeah.
What are the implications of potentially having a CTP symmetric cosmology or understanding the...
Okay. So what you're talking about is a specific model that came out, and it's a very speculative thing in terms of the details of the model of having two universes with different time directions. There's no evidence for that, but it might be, but there's no evidence for that. However, the CTP thing, violation, is a very important part of physics. This is something that's and actually,
I think it was discussed by Sidney Coleman.
Yeah. I mean, this is a very important. It's not only Coleman. It's one of, actually, it goes back to earlier. So I'll give you an example of something very important. If you look at particle physics, normally you find symmetry between particles and antiparticles. So, if you have an electron and a positron, you should have the same numbers. No? However, in the universe, we don't have that. We have asymmetry. We have normal matter. We don't have antimatter as abundant. I mean, in order to create antimatter, you need very, very special conditions, either in the lab or very special conditions in the universe, jets or something very energetic that collides with something else, creates momentarily some antiparticles and they disappear. But the universe as a whole has only normal particles, not antiparticles. But there's evidence that in the early universe, both of them, because the early universe was so hot, both of them were there.
Okay.
So in order to get to more particles than antiparticles, you have somehow to break this CTP. So there are three conditions that the late famous kind of physicist Sakharov, Andrei Sakharov, the Russian dissident at some stage, who was the father also the father of the hydrogen atom, of the Soviet hydrogen atom, but he became a dissident lately. He worked on this topic and he put three conditions called the Sakharov conditions for explaining why we have more baryons than antibaryons. And the evidence is that at certain phase there was a lot of baryons and antibaryons, roughly the same number. CTP, if these things are not violated, they would have the same number. But because we were left with particles, normal particles, not antiparticles, it means the symmetry has been broken. And the evidence for that we have is the number of photons per baryons. Let me explain this. If you look at the universe and ask how many photons it has per any baryon, per proton or neutron, that's what we mean by baryons, you find that the number is staggering. There's roughly about 10 to the 9, about 1 billion photons for each baryon. And this you can explain only by having a mixture of, there's the details that one has to go to, but roughly, you can explain this only by the fact that you had initially a lot of protons and antiprotons, neutrons and antineutrons, particles and antiparticles before protons and neutrons even. And those annihilated each other and formed and created photons. So that's why you have so many. But it so happens that the symmetry was not perfect. It's one of them was a little bit more than the other, and that's one that survived. So that is the evidence for this CTP. So it has, and this is not exotic physics. This is something that we see. Now, what is the implication of that? Cosmology creates all kinds of unusual models. If you look at, for instance, there's this phase in the universe, the very early phase. It's called inflationary universe, inflationary cosmology, where the universe expands in an exponential rate. It expands like crazy. In a very split of second, it grows by a factor of roughly 10 to the 30. So 1 and 30 zeros behind it, bigger than it was just a split second before. It just went boop like this. And this models, there's a family of models like this. And there are simple ones of them that we could rule out with the data. Now we rule out some of these models with the data. All the others that are left predict that you have multiverses. You have many universes all the time. And that's crazy. It's our universe is just not one universe. It's in this picture, at least. It's not the many world of quantum physics, which is very different. In this picture, you have this meta universe, which is this background universe that expands like mad. And in it pops all kinds of universes all the time. And one of these universes is our universe. So it's a crazy picture if you think about it. But this is what we are kind of concluding from the theories we have. Of course, our theories might be wrong, but our theories has been so successful. It's staggering how much success we had with Big Bang theory. What we call in the jargon, we called it lambda CDM, lambda cosmic dark matter model, which is really had incredible success. So you have to have another. Maybe our theory is wrong, but then you need to have another theory that explain everything we can explain and more, and much more kind of. Less crazy than this multiverse and all that stuff. So yeah, I myself don't like the multiverse picture. I must admit, but sometimes it's forced on you, and it might be right. I hope it's not, because I like other models. I like to. I think these multiverse issues is kind of creating a loophole in order to explain other things that you cannot explain otherwise. But
Okay.
but in this case, they come out naturally from the theory, and that's
Okay.
very hard to avoid.
So looking ahead, massive new projects like what you mentioned, the Square Kilometre Array, SKA, and ESA's Euclid telescope are on the horizon, promising even greater sensitivity. What leap forward do you anticipate with such arrays and telescopes in finally mapping out the epoch of reionization in detail? And what mysteries are you most excited to potentially solve?
Oh, that's we don't have enough time to answer all of these questions.
Bullet points. Bullet
So
points.
I'll answer. So let me start with the project. Euclid is already observing, actually.
Mm-hmm.
It has started looking at the universe. And excited, it's built for other things, but it will shed some light on the things that we are doing. It's not kind of designed for this, but it will help with us. SKA also, they started rolling it out. SKA, just to explain this, it's like LOFAR, as I said. You have these stations that are sensitive to certain frequencies. So SKA is something similar, but much, much, much bigger. So LOFAR costs something like 200 million euros, give and take. This will cost 2 billion euros. And it's a multinational collaboration that almost, all of Europe, most of Europe, China, India, Australia, South Africa, many, many, many countries are involved. The US is not. They decided they don't want to be part of it. So it's a multi-billion, not multi, but 1-2 billion euros or dollars kind of a project that will be based. Part of it will be based in South Africa. Part will be based in Australia. It has started rolling out, which means they're starting putting kind of detectors on the ground. Takes time to get to this. It will be much more sensitive than all of the other experiments that we have now. And also it has many targets. One of the targets is this cosmic dawn and epoch of reionization. This part of the antennas will be based in Australia. And that's where the activity is going on. And I expect in 10 years this will be. In this field, whenever you are asked when SKA will produce results, the standard answer used to be 10 years. So I have been saying 20. Every time I'm asked, I'm saying 10 years, 15 years. But now this is real because there's something on the ground. So I think 5 years will have the full thing there, and it will take some time to understand all its quirks and perks and all of that stuff. And it will kind of answer many of these questions. Okay. For instance, one of the challenges that we would like to say, and currently with LOFAR and other, we don't measure, we don't have images. Our data is not good enough to have images, so we construct statistics like something we call the power spectrum or other kind of statistics, which is a statistical statement about what you want to measure, about the underlying distribution of matter in the universe, hydrogen, ionized or not ionized, all of that stuff. SKA should be able to get images. You can say this part of the universe is ionized, this part is neutral. So you can say these types of things. Currently, you cannot say. So this is very exciting. And if you can do images and you can also push the envelope back in time, you can be more sensitive to the cosmic dawn, then you can probe the first types of, truly the first kind of dominant or abundant type of galaxies and their properties. So that's one thing. But also you can link better to the early universe. Okay. The biggest challenge is measuring the dark ages. Dark ages are incredibly challenging, and we cannot. And this you will love. We cannot do it from the ground. You have to go to space, which is your your love. And the reason for that is very simple. The atmosphere of Earth, the ionosphere of Earth, at these very low frequencies, there is something called plasma frequency. So if you have very low frequency, below 10 millikelvin, 10 megahertz frequency, and below 5, 3, 2, it comes to the ionosphere and bounces off, right? It's called it's because it's below the plasma frequency. So for it, the atmosphere is a solid object. It just comes and bounces back. So then you have to go to places where you don't have magnetic fields and you have much more stable things. One of them is the moon. So the moon is a very promising location from which to observe the 21 centimeter. Because if you remember, all of the difficulty I talked about, or all of the challenges, come from the ionosphere. And the ionosphere is something that has to do with the Earth. It's where the gas is ionized in our atmosphere, and it interacts quite rapidly and a lot with the magnetic field of Earth. The moon doesn't have these things, doesn't have that problem. So there is now a push to go to the moon, driven by politics as usual, by India and China going to the moon. So now the West wants also to go to the moon, and then when you go to the moon, you ask, what do I do with the moon? What type of things? And this is one of the first things people think about. You go and look at the 21 centimeter because there's no ionosphere, and then it becomes much simpler. Even though we have this synchrotron from our galaxy, but it's stable. I can distinguish between the two easily. Whereas now on Earth they are both dancing like this, and you cannot distinguish. You don't know what is what. So that's one of the things. Actually, one of my first postdocs, when I kind of got into this, somebody Grant Harker, who worked with me in 2007, 8, something like this, when we started this project. And he went very later to work on satellites that are around the moon to look at the So this is now a serious business, which is very promising. So this is very challenging. And why is it promising? Because why is it so exciting to go to and look at the dark ages? Because in the dark ages, you don't have stars, you don't have galaxies. So what you are looking at is a global phenomena that covers the whole universe. And so it's a truly cosmological phenomena. And if you can detect things in detail in the distribution of matter, the density, etc.,
fluctuations,
it reflects completely the initial conditions of the universe. It will be wonderful. It will be a treasure trove. It's decades from now, but it's something that I'm very excited about. And that's one of the kind of fundamental things that we need to understand. What are all the initial conditions of the universe, and not part of them? Because again, you want to understand how this thing came to be. It's if you think about the universe, it's fascinating. It's exciting, etc. But it's crazy as well.
Yeah.
So it has it gives you a direct handle into what was at the
Okay. The technology required for your research, like the vast radio telescope arrays, extremely complex signal processing, massive supercomputer simulations, is truly cutting edge. Do you foresee potential for these techniques, which are developed to decipher the faintest cosmic whispers? Do you foresee the potential to eventually spin off and benefit other fields, perhaps improving communication or remote sensing or data handling for future space missions or even applications here on Earth?
That's a difficult question to predict. But what I can tell you is that because of the multidisciplinary nature of this field, we had things that are we had all kinds of aspects that come from completely different directions that can merge together in this thing. So I can see things that are algorithmic development that might be useful. The way we used the GPUs, for instance, from the beginning was very novel, and I think people. I remember NVIDIA, which is the company that makes these GPUs. Back in 2008, I think they were so excited about what we are doing. They gave us lent us a few GPUs. This is really 2008, something like this, 7. It's really long ago. We were the first. Yeah. That's pre the AI kind of thing. So I'm one of the first people. I mean, me and my colleagues in the project were the first to use GPUs. Not for because people use them for games. We use them for number crunching, for real things. And actually, we put one of our PhD students on the GPUs to see the efficiency in doing some calculations, something called Cholesky decomposition, which has to do with matrix inversion. And he had to write report to the NVIDIA. And they actually invited him to one of the conferences in San Francisco that the CEO actually talked as a kind of, he was the keynote speaker for this. So they got excited about our project. I want to mention another kind of very fascinating thing that happened with radio astronomy, which also was unpredicted, which is the Wi-Fi, which both of us are using now. Wi-Fi is a spin-off of radio astronomy, and the reason is that it's a Dutch. I mean, the three of them that did this were working in a Dutch telescope. And one of them is Australian, who did the whole development. They were looking at black holes, and the radiation from black holes comes to these big dishes, and then it bounces off, and there's a building there, and it's called Westerbork, the telescope. That's the Dutch telescope. There's a building, and it bounces off. So you get all of this bouncing of radiation back into your detectors. So you have to clean them up. It's like the signal at home, it bounces off the walls that comes back to you. So they developed this technique called FFT on a chip, so Fourier transform on a chip, and they were able to filter it. So it's easy, you filter it. Once you have the Fourier transform, you do that Fourier transform. So one of them was clever enough to understand that this has a lot of implications, and he went into used that paper to further develop it, and now it exists in all our houses.
Yeah.
So you never know. Yeah, absolutely.
So cosmology inevitably touches on profound, almost philosophical questions about our place in the cosmos. How does your work contemplating the universe's immense history and scale influence how you view humanity's role or future within the vast expanse?
It's something I think about a lot. Actually, this is one of the advantages of working in cosmology, is that you can contemplate these questions as part of your normal work, which is exciting. So the first thing you learn, you face when you look at the universe, is how immense it is.
Mm-hmm.
And how insignificant we are. And this is not just words. This is real.
Mm-hmm.
I mean, it's just the universe. So just to give you some numbers, just to get to that. The solar system is located in the Milky Way, which is a galaxy. Mm-hmm. This galaxy has 200 to 400 billion stars like the sun. This is our own galaxy alone. To say we are special, that's just crazy. It's just, and we are in this place that is completely insignificant in the galaxy. It's on the outskirts, not exactly out, but not very central. And there's billions and billions of stars like us only in our galaxies. And if you look more and more in the universe, wherever you look, you find galaxies. The unit, so to speak, the thing that you see when you look in a telescope in the universe, you don't see stars, you see galaxies, which is kind of this. So we know we have trillions of stars in the observable universe. We have trillions of stars. So we are not significant in a significant place or location, and our sun is a normal star. It's not something too exciting. It's just a normal star. So you expect to have many stars that have planets that have similar properties to ours. And now we know that almost every star we look at, there is around it 5-10 planets, something like this. So you multiply the number I just mentioned by 10, and you get to the number of planets in the universe. It's just crazy. So in that sense, it is unusual. But it's unusual in many other things. We, as I mentioned, as an answer to one of the previous questions, we are the type of matter that makes us is only 5% of the constituents of the universe. That's just, So we are not special also in that sense.
Okay.
And if you go more speculative and say there are multiverses, then, there you go. There is, infinite universes as well. It's more than that. But even if you go back to Earth and you look at our history on Earth and you ask, when did humans come about? And so I recently wrote a book. I like writing books in Arabic, just because there are not so many scientists writing specifically in Arabic for the larger audience. Of course, my papers are all in English, but for these general audience things, I write in Arabic as a decision. And one of the books, the last book, was about life in the universe. So if you contemplate about life in the universe, I have this image there. Of if you give an analogy of the life on Earth as something that has a 24 hours cycle, and then you ask when humans came about, say Homo sapiens, we came in the last 6 seconds in the 24-hour, time life of Earth, which is basically this 24 hours are 4.55 billion years. So consciousness, the Earth didn't have consciousness until recently. well, not us only, but also mammals are conscious. There's lots of consciousness in there. It's not only us, but it's something that evolved recently in the last 500 million years or something like this. So most of the life of Earth didn't have conscious beings. The consciousness in the most basic level, like consciousness of animals, etc. But thinking beings, technology developing beings, civilization is in the last 10,000 years. So to say we are the center of anything, it's just crazy. So that's something that you learn immediately. And then you have to ask yourself, okay, so being a scientist, you don't think about religion, about other things as part of your daily tools, because you have to follow the evidence wherever it takes you.
And avoid bias or something.
You cannot bias yourself, even if you are incredibly religious, even if you're a devout person. When you go to your lab, you cannot use that as part of your scientific method. Scientific method that's one of the big assumptions. Nature exists by its own right and its own laws. Whether it's a correct assumption everywhere, that's debatable. But this is what you assume as a scientist. I explain nature by its own terms, not by my own terms, and that's very important. So in that sense, it's very important. So religion doesn't get in. And I'm Palestinian, Middle Eastern. So religion is very important all around here. But you cannot take that into being a scientist. I myself, I'm atheist. I don't think about this. I don't think there's anything outside nature.
Okay.
People like me that are more rationalist, more kind of materialist, if you will, in terms of our philosophical kind of outlook, have to answer all kinds of questions. What's the meaning of life? Because you have then, there's no, again, I mean, you have to pour meaning into your life. If you are religious or believe in a higher power, that's an easier thing to answer. You just say it. So I think we make a meaning of our lives ourselves. It's the way we live, the way we interact, the way we contribute, the way we live our lives is the meaning of our life. And I think that's a much more profound way of looking at life and more meaningful and more kind of satisfying way of looking at life than the other way that gives everything to us, to external power or whatever, and says, okay, I rely on this. Especially given the suffering that we see all around us. It's very, so you have to look at this in this way as a scientist. Of course, this type of science, especially this type of science of cosmology, makes you ask fundamental questions about the origin of all of it. What's our place in the universe? Do we? Is it a special place? Is it a special universe, and there are other universes that are not special? So there are questions that we can answer. There are questions that we cannot answer. But I certainly look at nature as all it needs to be, and there's nothing outside that.
Okay.
Which is what makes me, there are other scientists that believe the different ways, but this is the easiest way to understand. I find it, at least for me, to understand what my position and my place, and because otherwise you get to very, very strong contradictions.
Okay. Before moving to giving some advice to the students and professionals, I really have to ask this question. You talked about consciousness. When you as a science community look back into as observers, look back into the past, are we collapsing the reality into a state, or are we changing?
Yeah, you mean the quantum question about measurement?
Yeah.
Look, this is something. I'm not an expert on that aspect of quantum physics. But I'm interested in it, so I read about it a lot, etc. And of course, as a student of physics at the time, I had to plunge into. I think the way quantum physics is formulated classically, traditionally, is very, very problematic. And I think it's just crazy. What is called the Copenhagen interpretation is just something that is structured. Actually, historically, the people who formulated this, like Bohr, like Heisenberg, like von Neumann later, or Dirac, they belong to this philosophical school called positivist, logical positivist, which was very, very kind of influential in the early 20th century. This is what is called the Viennese Circle that developed. And one of their assumptions, at least one of the things that they kind of wanted to pushed, was that we cannot say anything about the universe as is. We only can say about measurements.
Okay.
So for them, it doesn't mean anything to talk about anything actually that beyond what you measure. If you, Einstein famously asked, "Does the moon exist?" When I don't look at it, I mean, he went to that, and Bohr's answer was maybe it doesn't exist. So it's crazy. I mean, this is. It has these elements that puzzle us. What happened in that field, as far as I can follow it, is that in the last 2 decades, many people came with challenges to the Copenhagen interpretation and started looking. They wanted a realist kind of understanding of quantum physics, so to make it say something about things other than measurement. What the electron does before we measure it. I want to know. In quantum physics, the classical way of measuring, you can't know. It's a meaningless question. Anyways, so in that field, there's a lot of development. And I like that. I like these aspects because I am a realist. I want to say something about reality, not just what I measure in reality. There were some even things that are, for me, I mean, with all due respect to others, it's just completely crazy to think that consciousness can decide what the universe is. Measurement can decide what is the outcome. That's just, it goes against anything I say in cosmology, because I have to assume that the universe had a history which I understand. Nobody was there to measure it in the universe. So all of this is just a myth until we get to the lab and measure it. It just doesn't make sense.
Okay. Gotcha.
But so it's this puzzle. Quantum mechanics is one of the most successful, is not one of the most, is the most successful theory that we know. Especially quantum field theory and quantum electrodynamics. Its accuracy is staggering. Yet it's so in terms of the equations and how they work, they seem to work well. What its meaning, the interpretation, that is still not clear.
Okay.
And there's lots of new ways to interpret things. There are people, for instance, in the 60s, I think someone came up with the multiverse, many world interpretation that Evert III, he came up with this interpretation aspect, which now it's more popular. There are other interpretations that try to keep reality as reality and not just measurement. But whether this is the last word, whether this is the deepest theory of nature, we don't know.
Okay.
But I cannot speak as a full expert on this. I rather not go into this. But as somebody who is interested in this, I think as a scientist, I want to know what is reality. Not only what I measure, but what is reality. And these guys that started this didn't want metaphysics as part of the deal. And now metaphysics is back into this. And metaphysics not in the sense of religion or something, in the sense of what is there. So you have to assume something. It's ontology, if you will. Okay. It's what is there in the universe. I have to assume something about what's there in order to understand, in order to formulate my theories. It's what's So I hope this is a coherent answer, but that's my view.
No. I appreciate your perspective. This is really important, which brings us also to my almost final question. Saleem, for the students and young professionals listening, perhaps inspired by this journey back to the cosmic dawn, what advice would you offer someone considering a career path in the challenging and rewarding fields of cosmology or astrophysics today?
Yeah, I mean, it's a very exciting field to start with. So I'm all for it. The challenge in every field in science is to pick up a field as a PhD, is to pick up a field that you make enough contribution to it or kind of significant contribution to the field so that you can continue as a scientist. So when one chooses a field to work, it has to be some type of compromise, but some type of not compromise in the following sense. You have to do what you like. That's to start with. But also you have to have a good eye to see in the kind of spectrum of things that you are kind of like to do, what is the thing that is developing. Don't go to a field that is very highly developed. It's very hard to contribute to these types of fields. Feynman used to say, you either go to a field that is new and small, and so you can contribute a lot because there's not many competition, or you go to a field where there are so many people working and very clever people, Of course, I'm paraphrasing, fine. But then you can contribute even only if you are as clever or cleverer than all of them. So I think the compromise is the best thing. Somehow to go to things that you like, the one likes, and that's the more important aspect. But then find these directions in that field where you can see development in the future. So if you go to a field that is completely mature and already, it's very hard to contribute things.
Okay.
Having said that, astronomy has been proven since ever. There's always new things, always. And sometimes it's surprising. I mean, now the most popular field in astronomy is exoplanets.
Okay.
30 years ago, it didn't exist. Nobody looked at it.
Yeah.
But then
and
suddenly, nature always surprises us, and that's nice. So always in astronomy, you always have things that you can contribute significantly to. But again, you have to follow your feelings and and it's a great career if you are successful. It's wonderful. I mean, it's a very privileged life, I must say. As I joked at the beginning, people pay me to think about these things that a normal person will have very little time to think about. Our position in the universe, where we come from, etc. I get the salary for that. Not exactly for these questions, but these are byproducts of the questions I think about. So that's nice. So that's my advice: is try to find a field that is evolving currently and it has a future. Don't go to fields that have already peaked, because then it's very hard to find your niche.
Okay. Before we wrap up, is there anything else you'd like to share with our audience? Any announcements?
Yeah, so we currently have a couple of papers that we just submitted. One of them has been accepted, and the second one is almost accepted for publication. Where there's a new upper limit, which has pushed the input down. I think the coming couple of years will be instrumental. Maybe more, 3 years will be very, very important, because we have improved our methods. We now in a completely different place than we were 10 years ago. So look out for this space. There's lots of excitement coming, and not only from us, but from other experiments as well. One of the things that when I got into this field, so I'll say something a bit more generic. When I got into this field, I thought I'll get in, 5 years, measure what I measure, and then move on. This was 2004. We are now 2021, and we are still haven't detected.
2025.
21 years later, we haven't detected the thing we wanted to detect yet, the signal we wanted to detect. But it has been an enormously enjoyable journey. It is the journey, absolutely. I mean, whoever said that, it's the enjoyment of doing things. That, of course, the discovery is ultimate pleasure, but it's a passing moment. You discover something, but then you want to continue. And you might get some fame from discovering, but the absolutely fundamental, a kind of deep pleasure you get from exploring the things themselves. And whether it gets you to a great discovery or a simple discovery or even non-discovery, at the end, it's the journey and the way you evolve as a person and as a thinker and as an intellectual, as a physicist as well during this. So it has been an immense kind of experience, and it continues. I mean, and I hope in the next 5-10 years we'll have much more to say about this.
Yeah. Professor Zaroubi, this has been, as you said, a fascinating journey back to the dawn of time. Understanding these first billion years helps us piece together the entire story of the cosmic evolution, which ultimately informs our place within it and the context for future space exploration. Thank you so much for sharing your insights and expertise with us today.
Yeah, thank you. Thank you.
To our listeners, join us next time on the Omar Alayli podcast as we continue to explore the science, technology, and engineering that advances space exploration. Until then, keep exploring.